Bismillahirrahmanirrahim. Before starting today's session, if you have any question regarding the last session or any part of the syllabus, you are most welcome to ask some question if you have anything to ask. Okay. So in the last part, we have discussed on the time variancy and time invariancy of a system. So the last topic was a time invariant versus time variant system. So from your last experience, probably in the from your last semester, you have also know about this, but I'm just trying to recall those things so that you don't have any sort of confusion on this term in future, because it is very important to understand both mathematically and as well as graphical representation with graphical representation. So we have mentioned these two terms. One is y n comma n minus k. That means that output is shifted by k samples. And another one is y n comma k. It means that your input is first shifted by k sample, and afterwards it is given to the system, and this is the output. So we need to know that there should be an equation like yn is equals to, let's say, xn plus xn minus 1. This is the equation. This is actually the system definition. You need to have this equation, and this is known that this is your system. And you need to evaluate whether the system is time variant or time invariant. That was the question. If they are equal, yn minus k is equals to yn comma k, then this is time invariant system. Otherwise, it is a time variant system. And we have also discussed on the example number 2.2.4 a, and we have covered up to this in the last session. Today we can start with another example. Probably you have gone through this. The system is defined as this: yn is equals to n xn. So what does that system do? It takes your input and multiply with the sample position. It multiplied with the sample position, the own position of that sample. Okay. So first of all, number one, we are shifting our output to for k samples. Yes, 69. You have some question.
So just to be sure, all the parentheses will be second bracket, right?
You are talking about this y, then n minus k?
Yes, sir. The representation will be second bracket, right?
No, not necessarily. Most of the cases, this is in first bracket. So we are using the second bracket or curly bracket in the cases when we are representing the series of data for a sequences, or like 1, 0, 3, 2, where let's say this is the 0th sample. In that case, we are taking the second bracket. For specifying the position of a sample like x3 means at the location of 3. So this is 0, 1, 2, 3. What is the value of x3? That is 2 for the uppercase. Okay. So always we are using the first bracket in that case.
Yes, sir.
Okay, thank you. Okay. So we are shifting the samples with the k samples. That means n is replaced by n minus k. So n will be again replaced by n minus k, and n will be shifted by n minus k, and that is good for us. That means our output is shifted by k samples. Okay, we'll take one example that will help us to understand the process. Okay, let me choose one input. Let's say this is our xn. I'm drawing our xn. which is looks like 1, 1, 1. Take a very simple example: 0th position, 1, and 2nd position. Okay, very simple. Now we need to draw the value of yn, how it should be looks like. According to the system definition, this is our system definition. What should be the first value? The first value is all the sample. This is 1. The height is 1. Okay. So what about y0? Y0 equals to 0 multiplied with x0. So 0 is 0, the n is 0, and then x0 is 1. So of course that is 0. So it starts with 0 at the 0th location. At the first location, we'll have y1 is equals to 1 multiplied with x1. Again, 1 multiplied with 1, so it will give 1. So the height will be like this. Similarly, you will find that y2, it must be is equals to 2 into 1, so that will give the value 2. So this is 1 and this is 2 at the location of 2. This is our yn. Now if you shift it for k samples where k is equals to 1, let's say k is equals to 1, what will happen is very simple. Since k is a positive value minus k, so it will shift it to the right direction for one sample. So we are drawing yn minus 1. That means yn minus k, where k is equals to 1. We are shifting it for one sample. So it will be 0, then 1 and 2. At the location of 0, that will be 0, 1, 2, 3. It will be shifted to the right. So this is this is directly you are having your output. This is your output, and output is shifted to the right for one sample. That is good. And you'll find that whenever we are doing this, that means this one, whether it is equivalent to this equation, that means I'm talking about this one. Okay, let me check it. Let me check it now. We are trying to find yn minus 1 for each position. We have already written that, we have found it from this equation, that it would be like n minus k, k means 1, and then x, n minus k, k is 1. Now if we want to find it, y at n is equals to 0, that means if we put n equals to 0, that is a minus 1, y minus 1 is equals to n. Let n is equals to 0, then it is equals to minus 1, and multiplied with x, n equals to 0, minus 1. What is the value of x minus 1? Any of you? What is the value of x minus 1? Any of you? What is the value of x minus 1? This is xn. Yes, 73.
Sir, undefined.
Whenever in digital system it is undefined, means it's 0. Okay, because you don't have any value, so you can say that those are zeros. Is that fine? Okay, so we can make that. Okay, this is 0. For which location? For n is equals to, for n equals to 0, that means y minus 1 would be 0. Similarly, if you go for y, for n is equals to 1, we'll find y0 is equals to, y0 is equals to, n is equals to 1 minus 1, and x, n is equals to 1 minus 1. So in that case, we'll also find 0 multiplied with x0. Since x0 is equals to 1, while however it is multiplied with the 0, of course, you will have the 0. If I prolong this example, with, let's say, y n is equals to, we'll take n is equals to 1, and here n equals to 0. Then now n is equals to 2, we'll have 2 minus 1, that is the location. And for that one, we have 2 minus 1 and x 2 minus 1. So it will have 1 into x. 2 minus 1 is 1. So it will give the location y 1. At the location 1, it will have 1 into xn. So at the location of n2, we'll have the value is equals to what? This is equals to 1. So at the location of n2, in the scale of n2, we are getting the value output is equals to 1. Similarly, for n is equals to 3, what you will find, y, whatever the case, we will find the right side, 3 minus 1 multiplied with x, 3 minus 1. So that will again give 2 into x2, and you know that x2 is nothing but 1. So 2 into 1, it will give the value 2. So in this case, we've got 1 and 2. So first of all, what we have done graphically, from xn, we have drawn the value of yn, and yn is shifted one sample to the right, and we have found it like this. And this is nothing but yn minus 1. In the next case, what we have done, we are putting the value of n for different places. Let's say for n equals to 0, n equals to 1, n equals to 2, and n equals to 3. For these 4 values, that is 0, 1, 2, and 3, these 4 values of n, we are trying to find what is the value of the right side. And we have found that this is exactly the same as yn minus 1. So it can be proven that in that case, yn minus k is equals to n minus k into xn minus k is justified both graphically and mathematical symbols. Always you need to draw it and justify yourself. Okay, so I believe that this is now clear that, okay, we can write it like this. Okay, so whenever the sample is shifted right, of course the place, the position, the multiplication factor, because you need to understand that this is the n is a variable and it depends on this n. That's why both n and this n will change simultaneously when we are changing it in the as a function. Okay, now in the second case, if we try to find yn minus n comma k, what is the consequence? First of all, xn, that should be shifted. That should be shifted here. And after shifting, then you need to put it to the system. So what is your system? Your system is yn, n into xn. So if I put our input to the system, what will happen? It will not change this n. It will take the value as it is, because it will only change this value of x, because it actually make hamper or change the value of your input, and input is multiplied with a value of n. It is multiplied with a value of n. So you will find the result as n into xn minus k. So in the first case, we got this result, n minus k multiplied with x n minus k. On the other case, n comma k is equals to, we found n into x n minus k. because the input is shifted and input is multiplied with a value of n. That is the definition. Input is now shifted and that will be multiplied with the value of n, and that is the definition. If I give the graphical representation, it will be looks like the same as previous. This is our xn. We have given this is 1, 1, 1, 0th sample, first sample, second sample. If we shift it, of course, we'll find like this: 0th sample, first sample, 0, 1, 2, 3. This is xn minus 1. After shifting it, put it to the system. What the system does, the system yn comma k, the system will definitely, the input is replaced by, now our input is n minus 1, of course, and it will be multiplied with the factor of n. That is the system definition. That will be multiplied, always that will be multiplied with n. Whenever, if I write it like this, if your input is like zn, what will be the output? In that case, zn multiplied with n. If your input is zn minus 5, then what is your output? Your output would be zn minus 5 and multiplied with n, because that is the system definition. So I believe that you can understand they are not equal, and that's why this is a time variant system. So this system is a time variant system. Okay, another example. This is very important because you need to understand that whether this is a time variant or invariant. If that is a linear and time invariant, only then you can go for some calculation. Otherwise, you can do those system calculation. Another example is yn is equals to x twice n. Okay, let me give detailed example of this one. So our system is represented by this. Choose a color. Back. Yn is equals to x twice n. What kind of system is this one? This is a downsampler, isn't it? In the last class, we have talked about this. This is a downsampler. Let me draw a simple xn. For understanding, we may take, okay, let me take 1, 2, maybe this is not visible to you. Red one, 1, 2, 3, again 2. So the values are 1, 2, 3, 2, and 1, and the locations are 0, 1, 2, 3, 4. This is our xn. That is our input. If you do the downsampling means you are having yn is equals to x twice n. Where give it to the system. So what will happen after having the downsampling? Of course, we'll have this sample, and this sample, because in between this sample will be cancelled and the third sample will be cancelled out. So we can write it very quickly. This is at the 0th location. At the first location, the value will be 3. The value will be 3, and in the fourth location, it will be like this. So this is 0, 1, 2. What is this? This is our yn. Yn. This is y. 1, 3, and 1. If you find it, if you have any problem to understand this, please raise your hand. After that, what we can do, we can shift it. We can shift it for one sample to the right. Okay, let me shift it one sample. So it will be yn minus 1. So how it should looks like? It looks like 1, 3, and 1. 1, 3, and 1. 0, 1, 2, 3. Fine. Now our target is to find the value yn comma k. Yn comma k. We have already found the graphical representation of yn minus 1. So if we want to find it, n comma k, first of all, we need to shift our input to the right. For how many samples? The same number of samples for one sample. So if we do it, definitely it will be 0, then it will be 1, this will be 2, and this will be 3, and then 2, 1, and that's it. 0, 1, 2, 3, 4, 5. And this is x, should take the black one, xn minus 1. Okay, now if we do the downsampling, so now what we are doing, this is the system has done this. Now we have our input shifted, and now input should be gone through this system. So it will be like we need to find yn comma k. So we need to draw the yn comma k, how they looks like. If I want to find it, so I have already this, downsample it. So we need to, we are actually drawing it and trying to understand it without the graphic, without the mathematical concept. Afterwards, we'll write the equation. So if you downsample it, of course, we are taking this sample, we are taking this sample and this sample. And we are not taking number 1, number 3, and number 5. So how it should looks like? Then 0, then 2, then 3 is cancelled. From the 4, it will be again 2. So since this is 2, little bit higher, this is 1, 2, 3, 2, and 1. And then after 2, there will be nothing because the 5th number is cancelled out. This is your y. This is your yn comma k, where this is the value 0, 1, 2, 0. There's a 2 and 2. So we have found this yn minus 1, and we have found yn comma k. So now we can write that yn comma k is not equals to yn minus 1. And that's why this is a time variant system. Okay, so this is from the graphical representation, you can prove it. Now, if I want to write it from the mathematical expression, so this is the system definitions are given. Now, how we can write n minus k? Can you write yn minus k? It will be x twice n minus k, and it is equals to x twice n minus twice k. Now I will ask you to match it with our example. whether this expression is true or not. Let me check it. Let me check it with our example. That means x twice n minus k is equals to 1. That's why this is 2. Now check it for n is equals to 0. For n equals to 0, this is n equals to 0. You will have 2 into 0 minus 2. So it will be x minus 2. So that is x minus 2 for n equals to 0. What is the value of x minus 2? Of course, that is 0. Of course, that is 0. Now come to the n equals to 1. If I put n equals to 1 in this equation, then we'll find x 2 minus 2, and that is equals to what? X 0. What is the value of x 0? Sorry. What is the value of x 0? That is 1. X 0 is equals to 1. And you'll find that this is your 1. Now, if you go for 2, n equals to 2, put the value n equals to 2 in this equation, and you will find that 4 minus 2 is equals to x2. And x2 is equals to nothing but 3. And we are having the same value 3 here. Now, put n equals to 3. Then it will be 2 into 3, 6 minus 2, that means 4, x4. What is the value of x4? That is 1. And you will get the same value here. So in that way, we can justify that this expression we have mentioned here, this expression is completely okay. Because graphically, we have already drawn it and we have write it mathematically here. And then we just prove it that, okay, they are working as the same. Now in the second case, so that was the equation. That was the equation. In the second case, that means how we can express the value y n comma k in mathematically, how we can express it. The input should be shifted x twice n Can you help me? What should be the expression of y n comma k? Y n comma k means first the input is shifted. Input is shifted and then you are putting into the system. What does the system do? The input is shifted. That means n minus 1, that is your input, and give it to the system. Then what the system will do? The system actually make what? X, this n, before the n there should be 2 because it will be down sampled. But what about this minus 1? Minus 1 is a constant. No constant particle will be made any impact according to the system definition. According to the system definition. So we can write it like x twice n minus 1 because there will be no impact to the delayed function because that is a constant value. Because this 2 is multiplied with the variable n, not to the delayed function. So we can write y n comma k is equals to x twice n minus 1. Now it's time to justify. Let's take n is equals to 0. That means we are targeting this sample. N equals to 0. Put n equals to 0, then we'll find x 0 minus 1. What is the value of x minus 1? Of course, that is 0. If you target n is equals to 1, it will be x 2 minus 2, that is x sorry, I made mistake. For n is equals to 1, it will be x 2 into 1 minus 1, that is x1. What is the value of x1? The value of x1 is 2, and you have also find here 2. Now, if you target n equals to 2, that will be x4 minus 1, that is x3. And what is the value of x3? That is nothing but 2, and you will get the same value here, x2. I have discussed it in detail so that if I give you any sort of example, you don't made any sort of mistake, or you don't have any sort of confusion to judge the time invariancy and time variancy of a system. Take it as an example, yn is equals to x n by 2. So take it whether it is time variant or time invariant system. Another one is yn is equals to 3 x n, whether this is a time invariant. It is very easy stuff, even though let's say 3n into x n minus 1, whether it's a time variant or time invariant system. In a system, if we have like x, I already know that, okay, definitely this is equal and time invariant system. But if you add a time non-invariant, so a variant system, then of course the total system is a time variant system, because this is already proven that this is time variant system, and this is time invariant system. Time invariant and time variant system, if you add those together, it actually gives you time invariant system. So in a system, if you have any time invariancy in any part of the system, it will convert it to the time invariant system as well. Okay. Any question at this moment? No. Good. Then linear versus non-linear system. I believe that you have already this idea as well. The linear and the non-linear system, how to find it linear or non-linear. This is also very important to understand the system properly. So in a very short form, what we can represent, if you have multiple inputs, you may multiply it with the constant a1 and a2, and then you can sum up those two together and give it to the system, and you have an output. And it can be represented by the equation as this. That means x1 multiplied with the constant, x2 multiplied with a constant, and you are adding those together and then give it to the system. Or what you can do, you can give your input to the system directly, multiplied with that constant. Your another input, give it to the system, multiplied with another constant, and then add it together. If left side is equals to right side, then this is a linear system. Then this is known as the linear system. And this is the graphical represent or block diagram representation by which you can present the concept of the linearity. In the second case, we have presented that you have the input, put it to the system, you got the, put it to the system and then multiplied with the constant. Similarly, in the second case, and then added together and you got the output. If this output and this output, they are equal, in that case, this is a linear system. Previously, we have checked whether this is a time variant or not, and now we are talking about the linear cases of the system. So linear system, of course, maintain the multiplicative rule and the additivity property. So if you have both of those, then we have the linear we can say that this is a linear system. We'll give the example as well. Okay. So the example is also given in the book, so please go through that. Very important concept is called the causal and non-causal system. A system is said to be causal if the output of the system, that means yn of the system, at any time n depends on only the present and the past inputs. That means xn, xn minus 1, xn minus 2. Don't be confused with that notation xn. Xn means that is the present value. Let's say x n, where n is equals to, you already have the sequences where x0 represent the present input. The past inputs are represented as x minus 1, x minus 2. Those are the past inputs. The future inputs are x1, x2. Those are the future inputs. In that way, this n noted as the present input. If n is equals to whatever the value, before those values are mentioned as the past input, and after those one is known as the future inputs. Here it's very simple to identify that. If we draw it, this is the location as the present inputs, and those are the location for the past inputs. So this is x0 location, this is x minus 1 location, this is x minus 2 location. Similarly, this is x1 location, this is x2 location. Sometimes we are representing like n minus 1. This is basically the xn shifted for one sample. But in some cases, it's also represent the sample position in the past location when n is given. So I believe that is very simple. That means our output only depends on the present and the past inputs, known as the causal system. If it is not a causal system, that means it depends on the present, past, as well as the future inputs, then it is called the non-causal system. In case that is known as non-causal system. Practically, in signal processing, all the systems are most of the systems are the causal system, because we are taking the data and we are making some calculation, like an averaging. What we are doing the averaging the present samples and the past samples. We have already took those samples. So this is the present sample and some past samples. We are adding those together and divided with the number, how many samples we have, and that gives us the average. We are not talking about the future sample. Whenever we are taking that data, that is the present sample. So in conventional process or signal processing, we do not need to think about the future data. But some cases we need to predict something. So in that case, we are putting some dummy data for the future and try to predict something. In that case, we need the non-causal system. We need to design it in the non-causal system. So that is a geographical signal, and the images. Geographical images can be mentioned as a non-causal system. In practical cases, let's say you have a sequences of data, sequences of images. So you already have stored those images. The image number, you are processing the image at this location. Let's say you are already processed this one, and this one, and this one, -3. So you are now at this moment. That means that at t is equals to 0. Before that, you already have this one, and this one. Now, in practice, if all the images are stored in your hard drive, you also know about this 1 and 2. That means those future datas are also in your hand. So for any sort of processing, you can also take this value and take this value to predict something. What I mean, by using these two samples, you are predict something. By using these 2 and 3 sample, you can predict something. But if you also take some future samples, you may predict something more and better. In that kind of things, people are using the non-causal system. So in future, when we'll talk about the Z transform, then we'll also mention you the aspect of the causal and non-causal system. But in a very short form, whenever you are taking only the present sample and the past sample, your output is only depends on your present sample, let's say x0, x minus 1, x minus 2, and so on and so forth. Then this is known as causal system. Otherwise, that is known as non-causal system. Please go through this example. It will make your life easy. Sometimes you may confuse with causal system and causal signal. The causal system depends on, I have already mentioned, x0, x minus 1, x minus 2, and so on and so forth. But what about the causal signal? The causal signal is a signal. This is your present sample, and these are the samples you are looking for, the future samples. The causal signals in a continuous time domain, this is a causal signal. That means the right-sided sequences. This is called right-sided sequence, right-sided sequence. So right-sided sequence is known as the causal signal. The left-sided sequence is known as anti-causal signal. Left-sided, that means the past sample. And the both-sided sequence is known as non-causal signal. Be careful about the system and signal. Though those are the definition, I will always request you to understand the system itself. Do not try to memorize the part. So whenever we are talking about causal signal, the signal is the right-sided sequences. Just try to understand that. The right-sided sequences. That means a common sequences, a voice sequence. A voice sequences. We are recording the voice. Is that a causal signal or anti-causal signal? Can you answer me? We are recording a voice like this audio lecture. Whether this is a causal signal or anti-causal signal. Can you guess it? Any guess? Causal signal or anti-causal signal? Our audio recording. Yes, 115.
Causal.
Yes, of course, a causal signal, because we are recording this signal and we are waiting for the future signals. We are always recording this one and waiting for the future. So our signal is definitely a right-sided sequence. Anti-causal signal is which one is already stored, and we are taking this signal. We are taking this signal. So this is the conventional way. That means you have a system. Let's say you have a system and you are giving your input. How the inputs are given to the system. This input given first, then the next input will given to the second and third, fourth and fifth, and so on and so forth. And that is the conventional way how we design the system. Sometimes for getting your output, you need the present input. Let's say, for example, you need the present sample. You need n-1, and you also need n+1. That means you need x0, you need x minus 1, and you need x plus 1. In that case, this system is known as non-causal system because you need both present, past, and the future. That is known as non-causal system. Similarly, in the non-causal signal, you also have the present input, past input, and the future input. That is the basic difference between the signal, causal signal, and the causal system. We are defining those terms. In future, we will use these terms very frequently, and you need to define it quickly. Stable versus unstable system. Stability is a concept. So today we'll talk about the stability of the system. It is defined as an arbitrary relaxed system is said to be bounded. Bounded means stable input and bounded output stable if and only if every bounded input produces a bounded output. For example, you have an ammeter. This is an ammeter where the maximum value you can measure is 10 ampere. Now you need to put some kind of input so that the maximum output is in between 0 to 10 ampere. If you put an unbounded input to your system is an ammeter. If your input is an unbounded, then there is no question about checking the stability of the system. So the first point is your input should be bounded. For the bounded input, if the output is bounded, then this is called a stable system. On the other hand, if your input is unbounded, your output could be bounded or it could be unbounded, but you can't check your stability of the system. So for a bounded input, if you have a bounded output, then this is known as bounded input, bounded output stable, or the stable system. So for checking the stability, you need to think about the input, bounded input. Another example could be very interesting. Let's say you are riding a car. Okay, you are riding a car, and what is the bounded input for that car? So let's you start with the speed. You are changing the speed, getting up the speed, and you are very close to 300 kilometer per hour. So this is a very high speed. And the company already mentioned that, okay, the bounded input, the maximum input or the speed of this car is 250 kilometer per hour. So whenever you cross this 250 kilometer per hour, it is the maximum limit for this car to show the stability. So if you are running with this 250, and if this car is working very well, in that case, you can say that, okay, the system is stable. The system means your car is stable. But if you are increasing more than 250 plus, that means 300 or 275, in that case, if the car is not working well and it is beyond its capability and unstable, you can say that the system is unstable, because the system is still stable for the value of 250 kilometer per hour. So always the system stability also depends on the value of the input. You can't say that, okay, the system is unstable. You can always say that the system is unstable because you are giving the input beyond the capability of that system. So in that way, you can say that this system is unstable. So first of all, you need to say that what is the stability. You need to define the stability from the input perspective. and then you can move, you can check your system. Okay. And there is an example from the book. You can go through that. Interconnection of the discrete time system. Now you need to think about, we have the knowledge of the time invariant system and a linear system. If they are both properties are there in a system, then it is called a linear time invariant system, or you can say LTI system. This is very important, LTI, linear time invariant system. Okay, if we have two systems in series, then we may merge those together as this, with the consequence, first we have this system, and then we have the second this system. We may also swap these two systems. That means first we are taking this, and second we are taking this. Could be equals to, first we are taking the system 2, and second we are taking this system 1. They are equal if and only if the system is a linear time invariant system, LTI system. So it will give a lot of advantage when we'll design the filters. Okay, in some subsequent sections or classes, you'll find that we can design our system more precisely if that is a linear time invariant system, because in that case you can swap the system. You can swap the system, and it will help us to design a effective system in future. And that actually mentioned in this literature, for non-linear, non-time invariant system, they are not equal. That means the process should be followed in a sequence. But in case of linear time invariant system, you can take any one first and any of those second, or you do not need to follow the sequences. Okay, another presentation of the system is the parallel processing. So you have this system parallel with this system, you can run those together, and then you can add those together here. And this is also for the linear time invariant system. Otherwise, that makes problem to the output. It is not common for other cases. Okay. Okay. So I believe that is good for today. In the next class, we'll talk about the resolution of DT signal, that means discrete time signals, into impulses. It actually prolonged to the convolution sum, which actually means us, or will give us the idea how we got the output from the convolution sum. So I would like to show you with a lot of examples with the graphical representation how the impulse response is responsible to give you the final output. I'm just throwing this question to the whole classes. Can you justify that your impulse response, by having the impulse response, you will get your output? Of course, you are having the impulse response, and you can get your output by knowing your input. But can you justify this with the graphical representation? What does it mean? Let's say you have the impulse response looks like this. This is an impulse response, HT. I'm putting T here because you have already this experience from your previous semester. If I ask you this question, do you know about this impulse response from your previous semester? What is impulse response? Any of you, please?
If we given if we give the input as an impulse, and the output we get is the impulse response of that system.
Okay, very good. This is your system, any arbitrary system, and this is your delta function. If you put this delta function to your system, whatever the output is known as the impulse response. For our case, if we put the delta function, that is delta n, and we are getting the output as hn, that is known as, let's say, of course, now this is the samples, not a continuous time. So this is our impulse response. Now my question is, if you have this impulse response and you have an arbitrary input xn, how can you, or from your previous experience, if you have xt and you have ht, can you justify it with the graphical representation? How could you find the value of yt? How could you find the value of yt? Can you do that? If you have the xt, if I have given you the value of xt, let's say xt looks like a sinusoidal signal. Okay, this is your xt, and this is your hn. Can you find the value of yn, where yn is equals to xt, sorry, not n, this is t, xt convolution of ht. Graphically, can you, yes, 73.
Yes, sir. We can do this by convolution.
By
Oh.
what?
So convolution theory.
Yeah, can you present it by the graphical representation?
Yes, sir. So at first we have to shift it one of these two signal.
Okay, so let me just see that. Please show me the whole class. Okay, so in the next class I will just give you this responsibility to show me how the output can be found by the graphical representation. Okay, you have this sinusoidal and you have, let's say, you ht looks like this approximately. You can take your data. Okay, and then by graphical representation, your task is to find yn, how the yn looks like. So after doing that, you can just send me email. By the email, you can send me. So as soon as you have done it,